All right, so the goal will be you will know how to multiply matrices by the end, and then also you'll know how to use matrix algebra to solve a system of equations with two variables. So you can add to your repertoire of elimination and substitution matrix algebra. And I'll show you how to use technology to do that. So multiplicative identity. Do you guys know what is the multiplicative identity for the real numbers? You know, there's a specific number that is known as the multiplicative identity. Yes, it is 1. Because what makes it the identity? What is the multiplication? Okay, that's what the multiplication is. When you multiply something by 1, it's the sum, right? So that's what makes it. So matrices have multiplicative identities. Multiplicative identity for a matrix, I'm going to have to do this in general first because we have different size matrices. But it has 1s on the main diagonal. So here's the main diagonal here. And then it has 0s everywhere else. So that's the main diagonal. It has 1s there. This is actually a 3 by 3 that I'm giving you as an example. The problem is the matrices come in different sizes. They could be 2 by 2, 3 by 3. The identity matrix is a square matrix, meaning the dimensions m and n are the same. But it's 1s on the main diagonal and 0s everywhere else. That's what the multiplicative identity is. Now, when it comes to real numbers, do you know what a multiplicative inverse is of a specific whole number? Like 3. What's the multiplicative inverse of 3? Yeah, 1/3 is. So that's what's special about real numbers is every real number has a multiplicative inverse. If it didn't, it would not be part of the field of real numbers. A field is a set that adheres to certain properties. There's several that you've been studying all since Algebra 1. You just haven't maybe known that that's what it takes to be part of that set. But one of those is that every element of the real numbers has a multiplicative inverse. The way we test to see if something is a multiplicative inverse of something else is that it equals the multiplicative identity. You follow that? So to test to see if 1/3 is the multiplicative inverse of 3, you would multiply them and hopefully get 1. Okay. Same thing with matrices. Suppose A is an n by n matrix. So n by n means it's square. So we're talking about square matrices. So suppose A is an n by n matrix. I kind of tried to break this into 3 different points here. If, and that symbol means there exists, if there exists an n by n matrix, say a to the negative 1, we call this A inverse. Okay, a to the negative 1, we call that A inverse. So if there exists an n by n matrix, A inverse, or A to the negative 1, is what it looks like, but we call it A inverse. This symbol means such that A times A inverse equals the identity matrix. That's what we have here. It's not m by n. M as in M&Ms. By n as in night. It's just I subscript n because it's a square matrix. We only need one dimension here. Okay. So if A times A inverse equals the identity and A inverse times A equals the identity, then A inverse is the multiplicative inverse. That's the same thing I just said about 3 and 1/3. Because 3 times 1/3 is 1, and 1/3 times 3 is 1, 3 and 1/3 are inverses of each other. You could say 1/3 is the multiplicative inverse of 3. So with matrices, it works the same way. If when you multiply the two matrices together, try in both orders, and you get the identity matrix, then that matrix is the multiplicative inverse of the other one. So
A inverse is what we call that. It's the multiplicative inverse. Now, it's very important with matrices that we have both of these statements. A times A inverse equals the identity, and A inverse times A equals the identity. Why is that?
Remember that. Does it matter the order in which we multiply matrices?
Yeah.
It does. You can get a different answer when you change the order of multiplying matrices, and we did see that the other day.
So, if we're going to test to see if two matrices, A and B, are inverses of each other,
it doesn't really matter which is the one you consider as the inverse. It's like 3 1/3, which is really the inverse. I don't know. But depends on which one you started with. The other one's the inverse. So here we have A times B. So to test whether those are inverses, we have to multiply them. In one, A times B, and then B times A. And in both cases, it must equal the identity matrix. The identity matrix for a 2 by 2 is just going to look like this. Okay? There's the 2 by 2 identity. So let's try it. A times B. So we're going to go -1, 3, 2, and -5. 5, 3, 2, and 1. If you're still having difficulties with multiplying matrices, you will need to make sure you get it now here. So here's what it says to do, and we'll write it out. It says take row times column. And as you do that, you're adding the different elements. So like the top left here, you're going to multiply that -1 times the top left here, the 5. And then you're going to add to it the second element in the first row, which is 3, times the second element in the first column, which is 2. So it kind of goes like this. Row times column. But that's not the whole story. You're adding the elements. It's row times column to get that top left element. So it looks like this. -1 times 5 plus 3 times 2. And that calculation gives you the top left element of A times B. All right. And then the next row times first row times second column. It's going to be -1 times 3 plus 3 times 1. And that's the second element of the first row. By the way, just as a review, what's the order of this element here? Or of this matrix? 2 by 2, and this is a 2 by 2. The inner ones must match to be able to multiply them in the first place. The outer ones tell you the dimensions of the new matrix. I think that's helpful to know. It's helpful to know what size matrix you're going to end up with as you go through this process. So the next one, second row times first column, would be 2 times 5 plus -5 times 2. And as you look in the parentheses here, you should see matching elements if you've done it correctly. So that's a way to check. And then I have 2 times 3 plus -5 times 1. So my new 2 by 2 matrix that I get from multiplying A times B is -5 plus 6 gives me a 1. -3 plus 3 is a 0. 10 minus 10 is a 0. And 6 minus 5 is a 1. So A times B gives me the identity. So A times B gives me the identity. Now let's switch the order. Here. So I've got 5, 3, 2, 1 times -1, 3, 2, -5. I'd like you to try it. Now go ahead and multiply these two together. Try it on your own. You have to do the multiplication. Yeah, as we tried that, we see that, yes, it does give me the identity. And so my statement would be something like this. It's kind of like a proof, more or less. Since
A times B equals B times A equals the identity subscript 2. And in other words, the 2 by 2 identity. So we get a sense statement. AB equals BA equals the identity. B is the inverse of A. We should say multiplicative. All right. So in an effort to give you a chance to try some multiplication on your own, and check now, we're going to check a 3 by 3. So what you're looking for is when you do G times H, and you multiply them together, you should get this, if you even have a chance to get an identity. If one of these elements does not match that identity, then you're done. You can say they are not inverse. So I'd like you to try this. I'm going to come around and check to see how you're doing on multiplication. So I'd like you to try G times H and H times G, and then we'll talk about whether or not H is the multiplicative inverse of G. Okay, so we're going to multiply these two together on the calculator. 3 by 3. So we're going to take, and here's what you do. We're going to enter, I called it matrix G. If you go on the TI-83, there's a matrix button. On the 84 and newer, you have the matrix button is above X inverse in the first column, 1, 2, 3, 4 buttons down. So you hit second X inverse, and there's our matrix menu. You can see that we have a G and an H in here. Actually, let's go use G and H. Why not? You may or may not have anything listed in your matrix menu. If you have never used matrices on the calculator you own, you won't have anything listed in there. So you can see my matrix G and H I have not ever used. What we're going to do is edit the two matrices. So go over right arrow to edit. Does anybody need help finding the matrix menu? Did you find it on yours? Oh, on your, what did the calculator do you have? It should be, if you have the TI-83, it's just a matrix button on there. You don't have to go second. It's great. Oh, yours is that way. Okay, so it's second. Yours is the plus. And then matrix edit. Go over to edit. And we are going to select matrix G, that's number 7 on there. So you can just hit number 7. And then you need to tell what size matrix you're about to enter in, and it will give you a table or a matrix with that many cells in it. So 3 by 3. 3 by 3, yes. Matrix G is 3 by 3. And then we're going to enter in the elements of matrix G, which are -1. And it's going to enter them in straight across the rows. So -1, -1, -1. And hit enter, it will go to the second row. 4, enter, 5, enter, 0, enter. And then 0, enter, 1, enter, -3, enter. So we have now populated matrix G. Okay, now go to second matrix again. Go over to edit. Select matrix H, which is number 8. Change it to 3 by 3. And then we're going to populate matrix H. It's 15. Enter. 4. Enter. -5. Enter. And then -12. -3, 4, -4, -1, and 1. So we've populated the matrix. Matrix G and matrix H are populated. So now any operations we want to do with these, if you wanted to add them, if you wanted to scalar multiply them, if you want to multiply them, all this can be done on the calculator. We need to quit out of here first, or quit out of the screen. So hit second and then mode. Quit out of that. Maybe clear your screen if you need to. Now we're ready to do some math with matrices. Okay? Do you need help on this? Okay. So once again, second matrix, and then you have to go to edit and select matrix H, and then populate it. Okay, and then we
if you want to do math with the matrices, well, there's a bunch of math you can do. Under the math menu, these are a bunch of different operations on matrices that can be done that we aren't going to talk about. But if you go to names here, all we want to do is select matrix G, so hit number 7. And matrix G will pop up on the screen. Then go to second matrix again, and select matrix H, which is number 8. So you just type in under names, or select under names, the matrices you want to multiply, hit enter, and look at that, which is the identity matrix. Okay, so once again, go to second matrix. Does anybody need help editing the matrices? Okay, you have to first enter in all the elements of the matrix. Okay, next step. I'm going to now multiply H times G. And so to multiply H times G, you just have to select under the matrix menu and names, matrix H, which is number 8, and then go to second X inverse, that's the matrix menu, and select matrix G, which is number 7. Then hit enter, and out pops another identity. So I've just proven, via technology here.
I think I accidentally made them both the same thing somehow.
How would you
Yes.
delete a matrix?
Okay, we're building up to, so one of the prerequisite skills would be that you can multiply matrices. We're building up to solving a system of equations with matrices, which we'll do on the calculator. But you know, when it comes to 2 by 2 or 3 by 3, you could probably do this by hand. But the theory goes way beyond 3 by 3s. Okay. Determinant. I think you talked about this last year. Cramer's rule. So within the context of Cramer's rule, you are calculating determinant. So a determinant and inverse of a 2 by 2 matrix. Here's my generic 2 by 2 matrix, A, B, C, D. The formula for the determinant of a 2 by 2 matrix is we multiply the diagonals here, A times D minus C times B. That's the determinant of a 2 by 2. We'll talk next time after break about the determinant for a 3 by 3. We're not going to get to 3 by 3s today. But it's built off of this formula for a 2 by 2. You actually select an item, cross out row and column of a 3 by 3. You're left with a 2 by 2 matrix. And you have to do that over and over and over again. So it's kind of a recursive process here, one inside of the other. So this is the determinant, and this is the formula for the inverse for only a 2 by 2. Okay? So a 2 by 2, you take 1 over the determinant as the scalar multiple of the following matrix. You swap on the main diagonal, swap A and D, so you can see A and D have been swapped, and you negate C and B. So that is the formula for a 2 by 2 matrix, calculating its inverse. Now, the matrix, so, goodness. So here, it only has an inverse if the determinant does not equal 0. If the determinant equaled 0, this term out in front would be undefined. So that's more theory. A way to check to see if a matrix is invertible in the first place or has an inverse is to check the determinant. And if it doesn't have an inverse, you're not going to be able to solve equations with it. There's some kind of a relationship, a dependence relationship, or just no solution. All right. So let's go ahead and calculate the inverses of some of these matrices. I'm going to have you do this in the homework, so you want to have some examples of this. Just using the formula. So the determinant of this guy is equal to 2 times 3 minus 5 times 1. So 6 minus 5 is 1. That's an easy determinant to work with. Determinant equals 1. So A inverse in this case would be equal to 1 over the determinant, which is 1, multiplied by, we swap
here on this main diagonal, so we're going to swap the 2 and the 3. The 3 will go up here, the 2 down here, and negate the 5 and the negative 1. The formula up at the top. And so A inverse, in this case, is the matrix 3, negative 1, negative 5, and 2. So we just find the determinant. We swap the 2 on the main diagonal and negate the other 2, and then multiply through by the determinant. It's a pretty easy process for calculating the determinant of a 2 by 2. By doing what we did earlier, multiplying the 2 together to get the identity with the generic matrix A, B, C, D, E, F, G, H, and getting the formula. So they came up with a formula. Obviously they have one, because you can take any matrix, type in matrix, and then hit the X inverse key on your calculator, and it will calculate it for you. And it will do it for a 3 by 3. And you'll see the power of technology on that, because a 3 by 3, the formula, it's difficult. It becomes difficult very quickly with these matrices to calculate the inverse. There's a process to go through to get it. B here, let's see, the determinant is, we're going to do negative 1 times 4 minus 3 times negative 2. So I get as a determinant, negative 4 plus 6 is 2. And so B inverse is equal to 1 over 2. Swap the 4 and the negative 1. So 4 goes up here and negative 1 down here. Negate the 3 and the negative 2, so it becomes negative 3 and positive 2. And then in terms of your calculator, it's not going to leave it in this form with a scalar multiple out front. It's going to distribute that through. So 1/2 of 4 is 2, half of 2 is 1, half of negative 3 is negative 1.5, and half of negative 1 is negative 0.5. And we'll do that one on your calculator in just a minute. I'll show you what that looks like. Calculator can do it really quickly and easily. C equals. So we go to calculate the determinant. 10 times 1 minus negative 5 times negative 2 ends up equaling 0. Okay, thank you. Ends up equaling 0. And so, what does this mean? C does not have an inverse. Let me just show you something here. Take this second row. If I multiply the second row by negative 2, and what do you get? Multiply this negative 5 by negative 2, you get 10. Multiply this by negative 2, you get negative 2. So this is just a multiple of this. It would be like solving a system of equations, but one equation is simply a multiple of another. If you graph two linear equations and one equation is the multiple of another, what will happen when you go to graph them? They'd be the same line. Yes, they would be the same line. So how many solutions do they have? Infinite. There's an infinite number of them. So what this is saying is this is not invertible. You're not going to find a unique solution if you use this matrix to solve the 2 by 2. All right. On our calculator, so let's go ahead and do this on the calculator. Let's calculate the inverse of B and see if it matches up. So going back to your calculator, go to matrix. We're going to edit matrix B. So matrix B is going to be 2 by 2. Okay. So 2 by 2. And matrix B on here was negative 1, negative 2, and then 3 and 4. So negative 1, negative 2, 3, and 4. Okay. And we're going to hit second mode to quit out of here. Okay, second mode, and then go to the matrix menu and select number 2. And all you do to find the inverse of this is hit the x to the negative 1 key. And that's what it looks like. So B inverse is 2, 1, negative 1.5, negative 0.5. Okay, so one more time, we go to the matrix menu. We go over to edit. Number 2 is our B matrix. We type in the elements of the matrix. We quit out of there. And then to select matrix B, we go back to the matrix menu. Under name, select matrix 2, and then hit the X inverse key, and that will give you the symbol for inverse. Hit enter, and that gives you the matrix. So you can check all of your homework this way, guys. You can check all the multiplication that you did on LA number 4, and this is the top row of your worksheet you're going to get today, is calculating the 2 by 2 inverse. I'd like you to do it by hand first, because you'll be expected to know how to do that with the 2 by 2 only, okay? But then check it with your calculator.
So we're only doing the top.
No, you're going to do it. Okay, I'm going to hand out a separate worksheet. I know it's on the back side of LA 4, but I'm going to give you
Another one?
a separate worksheet in your algebra number 5. Yeah. But I'm going to ask you to calculate inverses. All right. So where are we headed with this? Let's go to the next page here. This is the key. This is the key. We have this key equation here. This is called a matrix equation. This is the key. AX equals B. I'd like you to write that on the very top. AX equals B. Okay, AX equals B. Here's the parallel to this. If I had something like 3x equals 6, how would I solve for x? I would divide by 3. Which, yes. It's another way of also saying I can multiply by the multiplicative inverse 1/3, right? So divide by 3 or multiply by 1/3, x would equal 2. Same deal here. The thing is, you can't divide by a matrix. It makes no sense. What we do is kind of like what you do with trigonometric functions. You multiply on the left by the inverse. So the solution to this equation is A inverse of AX equals A inverse of B. Does it matter that A inverse is on the left of B? Yes, it absolutely does, because matrices are not commutative. A inverse A cancels out. That gives us the equation x equals A inverse B. So what does that mean for solving systems of linear equations? If you could write the system of linear equations in terms of matrices A and B, you can solve for x and y, as long as A has an inverse. If A doesn't have an inverse, you're back to your substitution elimination. You've got to find the dependence relationship, because you don't know if it's infinite solutions or if it's no solution. They could either be parallel lines or one line on top of the other. Remember the 3 cases? This is only going to work if there is a unique solution for x and y. So now here's how you set this up. Matrix A in this case is equal to the coefficient of the variables in standard form. So matrix A is very intuitive. 5, -4, 6, -5. Completely makes sense, I think. It's the coefficients of those. Yes. Okay. Coefficients of the left-hand side. This is a 2 by 2 matrix, by the way. Matrix B is a column matrix made up of the answer column, which is a 2 by 1. See how I got the 2 and the 1 for matrix B? Okay, that's the answer column. So my matrix equation would say A x equals B. Well, in this case, A is the matrix 5, -4, 6, -5. The matrix X, which I'm trying to solve for, are the variables X and Y, just as they were on the last part of the worksheet on your homework. X was the top, Y was the bottom, and those were representing coordinates of your shape. Equals B, well, B is 2, 1. So I've just translated this system of linear equations into a matrix equation. Now, what the matrix equation says is that x, which we know to be the column vector x, y, or the coordinate x comma y, is equal to A inverse B. So if you know A and you know B, and your calculator can calculate the inverse of A and multiply that by B, you can get the solution quickly and easily using technology. Now you can't appreciate this if you've only solved 2 by 2s. But you have at least seen 3 by 3s, and I think you've solved it by substitution, elimination, combination of those two. Multiple steps. Now imagine that with a 4 by 4, a 5 by 5, right? You weren't asked to do it because it'd be terrible, yeah. Now the calculator can handle this very quickly and easily, and it handles 3 by 3s quickly and easily. So even in calculus, when 3 by 3s maybe show up occasionally, this is a method you could use for solving them that's much more efficient than what you're using in algebra class. So go back to your calculator. We're going to type these in. Back to the calculator. Go to the matrix menu. Go over to edit. Just so that I don't confuse you, I'm going to overwrite matrix A and B. So we're using matrix A and B here. So 2 by 2 matrix A. I'm going to enter in 5, and then -4, and then 6, and then -5. That's what we call my coefficient matrix. The left-hand side of the system of linear equations. So we're entering in matrix A. Alright, now go back to the matrix menu, second matrix, go over to edit. We're going to edit matrix B, which is number 2. And matrix B is actually now 2 by 1. So when I change this to 2 by 1, you'll see that the matrix size will change. 2 by 1. And my answer matrix was a 2 on the top and a 1 on the bottom. So that's my matrix B. Right, quit out of there. Now we're going to do our matrix equation. So we go to second matrix. Under name, select matrix A. But I'm not multiplying matrix A times B. I'm multiplying A inverse times B. So I hit inverse. So A inverse, and then I go to second matrix. Select matrix B. Hit enter. So A inverse B. You're going to type in the same equation every time. All that changes is the matrices. And there's my answer, 6, 7. So, what does that mean? Yes, we have a solution of 6, 7. That's where the 2 lines intersect. Okay. So the only thing you have to be aware of, and we're not going to, if we need another example, we can, but we're not going to solve this one. You can try it on your own. You just have to be aware that the left-hand side must be in standard form. Okay, ax plus by equals c form, or this isn't going to work. So number 7, that's the point of this one. I would have to rewrite this. The top one is fine. The bottom one has to be rewritten as 2x minus 3y equals 1. Now it's set up. My matrix equation in this case would be 4, -7, 2, -3. Inverse, let's just skip to the end, right? Inverse of that times -3, 1, and we've got it. Now, by hand, could we calculate the inverse of this 2 by 2? Yeah, it's pretty simple. And then multiply by this? Yeah, we could do that by hand. But the power in this is the theory. This could be 100 by 100 if we wanted to. And a computer can handle that, as long as it's invertible. Yeah. So, last example on here. I gave you an example of a real-life example last time. That was the transformation. Okay, transformational geometry can be done with matrices. Pretty powerful, especially when you start thinking about computer programming. It's a very powerful way to do transformations with matrices. You've used matrices if you're in AP statistics to do the chi-squared test. Okay, you use matrices there. Here's another example. Back in, well, I think towards the end of World War I they had figured this out, but this was a way to encode messages and use matrices. And because of the advent of computer technology, although it would fill this room, probably the computers in the 40s, but they could do calculations like our little handheld would do here. And you could use that to send messages. So we're going to go ahead and create a matrix to go with the word math. So it looks like this. The letter M, that is the 13th letter in the alphabet. A is the first, T is the 20th, and H is the 8th. So what I'm going to do is create a little math matrix. I'm going to say math equals the following matrix: 13, 1, 20, and 8. And so I'm going down. And you could decide to go across. It would just change it up a little bit. You just have to know that when you go to read the message. But I have M-A-T-H. So there's my math. Now to encode this, what we need to do is multiply the matrix by some invertible matrix, anything you want. You come up with any, you can just randomly choose a matrix, check to see that it's invertible, and then use that as your multiplier. So we multiply, I'll write that down, multiply by some invertible matrix, and that will give us a new matrix which encodes this. It gives you this scrambled thing. So we take, let's just make one up. I made one up earlier, so here's one that I know is invertible: -2, -3, 3, and 4. So I came up with that matrix. I know it's invertible. I'm going to take this matrix right here, -2, -3, 3, and 4. I'm going to multiply it by my math matrix, 13, 20, 1, and 8. You do that on your calculator. You multiply them together. It's not hard to do. You get this new matrix that means nothing to people who might try to break this code. Unless they have the coding matrix, it means nothing to them. So you come up with -29, -64, 43, and 92. And this is called the coded matrix. So I've encoded it. Taken this special message I'm going to send to you here for math and multiplied it by some invertible matrix and created a new matrix. So this is the coded matrix. It goes to somebody else who knows what my decoder is here, okay, or knows what it is. So then the final, we find the inverse of the coding matrix. Find inverse of this. Once again, this is the coding matrix, and the end result is the coded matrix. So find the inverse of coding matrix. So -2, -3, 3, 4, inverse. We do that, of course, using technology. We could do it by hand now. You're going to be asked to do that on the homework a bit. But the A inverse ends up equaling 4, 3, and then -3, -2. So we've got this coded matrix, and to get it back to this matrix, what do you think I have to do? Multiply by the inverse. That undoes it. So we take the 4, 3, -3, -2, multiply that by the -29, -64, I got it right up here, 43, 92, and that decodes it. So the inverse will decode it. And we get 13, 20, 1, and 8, and we go, oh, it's M-A-T-H. And you could add in, is the best, or it's great. Will help you to many things in life. All right.